Welcome back everyone to chapter 3 of genetics. Today what we're going to go over is essentially how do we figure out where genes are located. So we've already talked about Mendel and his laws of segregation and the independent assortment law, but he didn't really know where these alleles are located on, or these genes. All he knew was that these genes are being passed on from one generation to another somehow. It wasn't really until someone came along called Thomas Hunt Morgan and Calvin Bridges that they've come to a conclusion about this. So what they did back in the day was they took some flies. They had a female that had red eyes and a male that had white eyes, and they crossed them together, and then they ended up with all the flies being red colored, which was normal compared to Mendel's hypothesis, right? So everything appears normal so far. And then what happened was they crossed the female red flies together with the male red-eyed together, and then what they ended up with is something that we didn't really ever expect. So what we expected to see was a 3-to-1 ratio. So we expected to see a 3/4 of the flies to be red, which should be equal between males and females, and then 1/4 of the flies should be white colored, and that should be also equal between the males and the females. But however, what we're getting over here is that we're getting a 1-to-1 ratio between the males for the red color and the white color. And then over here for the females, we're actually getting all of them being red. So this was unexpected. And like with that information, it sort of didn't go along with Mendel's data that he had before. So like what conclusions can you come up with this? And what he did was pretty genius. He used something called a reciprocal cross. So a reciprocal cross is basically you would take the exact same two phenotypes that you were crossing before, but you're switching the sexes now around, where the female now is white, but the male now is red. Okay? And then from this reciprocal cross, if you get different results in your F1 generation, or even in your F2 generation, then therefore this trait is sex linked to the sex chromosome, instead of it being an autosomal, instead of it being a gene that isn't located on the X chromosome. So yeah, so basically that would be a reciprocal cross. And you're using this to determine if a trait is sex linked. So you're using this to determine if a trait is sex linked. In other words, these traits are being found on the X or the Y chromosome of these animals. So the way how you would do a reciprocal cross, as I mentioned, you're going to change the sexes from the original cross. Change the phenotypes. So what you're going to do here is, let's say if we had a female red that had red colored, and then we had a male that was white colored. In a reciprocal cross, what you're gonna do is you're gonna flip these around. You're gonna cross a female that is white colored, and you're gonna cross it with a male that is red colored. And then if we get different results in the F1, then therefore this trait is being passed on through sex linkage. So the reason why this was important for our question for genes that are being carried on chromosomes, what one of his grad students noticed was that you would take these crosses, and then most of the time you would get results that according to sex linkage you would expect. But one out of every couple of thousand tries, every couple of thousand offspring, you end up with some of them being lethal, and then some of them also having more than one chromosome, or some of them having only one chromosome. So basically, what you can come up with this conclusion is that without these chromosomes that have been removed from these two gametes, all of a sudden now you have a situation where you end up with exceptional individuals that are different in phenotype than what we expected them to be. And some of them are dead too, due to the lethality of you not having any chromosomes at all, or just a single Y chromosome, or even having too many X chromosomes as well. So this was their conclusion, that genes must be passed on from chromosomes, simply because of the fact that if there's a non-disjunction in meiosis, you end up with a incorrect balance of chromosomes in the next generation, which can result in lethality or other exceptional phenotypes that you've not expected it to be. But other than that, another important thing from this section is to understand the different kinds of sex linkage that we can have. You've already seen some of these, which is, there's two kinds. There's X-linked genes, and there's Y-linked. So with X-linked genes, you can have X-linked dominant traits, and then you can have X-linked recessive traits. For Y linkage, because individuals most of the time only have one Y chromosome, there really isn't any dominance or recessive, because there's only a single Y chromosome in a genome. So if you have a certain trait that is due to Y linkage, you'll always have it, and all the males will always have it too. Okay, and that's basically that. But the question is, how do we've already talked about product rule and sum rule. How do we figure out, how did Morgan get all the data that he got from these following crosses? So let's do that. So let's say we have a true breeding female that is, we're gonna say that X plus is dominant to XW. So what we're gonna do is, let's say we have our parent, which is a female X plus, and then we're going to cross that with a male that is X little w Y. So if you're X little w, you're going to be white colored, and then if you have both pluses, you're going to be red colored. So what you're going to do, again, just like before, the law of segregation, each of the gametes from the female, you would have a half probability of getting both of them. In other words, you also have a 100% chance of getting X plus, because you would have a half chance to get this chromosome or this gamete, and then half a chance to get this gamete. Because they're the same thing, you would add them up together to get a 100% probability of getting X plus. Now the male is where it's different, where you have half a chance to get the X little w and half a chance to get Y chromosome. So to calculate what the following phenotypic proportions you're going to get from this cross, you would have a half chance to get X plus X little w, and a half chance to get X plus, and then Y. So all of these individuals will be red, both the males and the females. So let's say we cross these together now. We're going to do the exact same protocol. We would have a half chance to get this gamete. We would have a half chance to get this gamete over here. And then from the male, half and half again. And basically from the male, you're always going to get a half chance to get both of them, because the male is always going to be hemizygous. So if you cross these together now, and if you're not familiar on how to cross these over, I'll quickly show you using the matrix method. So basically what you will get here is a 1/4 chance to be X plus, 1/4 chance to be X plus, Y. And then from the other one, you would have a 1/4 chance to get X little w, X plus. So basically X plus little w. And then 1/4 chance to get X plus Y. So basically what you're getting over here now, oh, my bad, this is supposed to be a little w. Yes. So basically what you're getting over here is you're getting all these females right here. They both have the X plus allele, and X plus is completely dominant to XW. So both of these, you would have all your females being red, and then your males will have a half chance to be red or half chance to be white, which is what he got over here. So that's basically a general gist on how you can calculate the frequencies using product and sum rule for X linkage. And that's it. Hopefully this helped.